That 5 dynamics, page 63, first question 31. And it's just based on the idea of conservation of energy, that all of the potential energy that it would have from the top would be converted to kinetic energy. So the simple answer for A is just 300 joules. Then we can use that to work out the speed. So if there's 300 joules as our kinetic energy, we know the mass of the object is 0.1 kilograms. We're being asked the velocity. Speed and velocity are the same here because it's going in the same direction. So our formula there that links these together, EK equals a half mv squared. 300 is a half times 0.1 times v squared. Remember in the worked examples I did for these, simplify what you can. So 300 equals 0.05 times v squared. Get what you're trying to work out onto the left hand side. So 0.05 times v squared equals 300. And then get v squared on its own. We'll worry about getting v in a second. So v squared is 300 divided by 0.05. Calculator out is 6,000. And therefore v is the square root of 6,000. Calculator once again. And there's our answer for B. For C, remember I said in the questions, this first question actually assumes that G is 10 to get the answer. So once again, for potential energy, this time the mass is 1 kilogram. We're going to take G equals 10 just for this question. And the height of the Eiffel Tower is 300 metres. This is a fairly straightforward. We're being asked potential energy. So EP equals mgh equals 1 times 10 times 300. And that gives us the EP. It's 3,000 joules. Underline final answers, just to make it clear. And then for D, we'll just do a similar calculation. We'll assume that all of that EP transfers to EK. So EK is 3,000 joules. The mass is 1 kilogram. And we're being asked V. So the formula links these together. And just like we did before, simplify what you can. Rearrange onto the left hand side, so I'm just swapping sides there, nothing fancy. Get v squared on its own, so do the opposite of what's is with v squared just now, so it's times 0.5, so divide by 0.5. And we get v squared equals 6,000 again. So v is the square root of 6,000, and we get the exact same answer again. And that's what you're expected to comment on in part E. Okay, so both velocities are identical, i.e. the mass of a falling object doesn't affect its speed, the velocity. Now, one key assumption behind that is in the absence of energy losses, things like air resistance. The larger mass has a larger potential energy, yep. But needs a larger kinetic energy. So the fact it's got 10 times the potential energy doesn't mean you get 10 times the speed, because the mass also appears in the kinetic energy formula. So it needs a larger kinetic energy to travel at the same speed. Or velocity. So, on to question 32, and basically what we're kind of doing is in one step doing what you did for the previous one. So we don't appear to be given a lot in this question. We've got a mass, we've got a height, and we're being asked a velocity. But the key to it is this idea that if it's dropped, then you've got conservation of energy, which can link these two ideas together. So we can say that the potential energy it has at the top must equal the kinetic energy it has at the bottom. Potential energy we can work out from mgh, and it must equal the kinetic energy, a half mv squared. So now we're ready to start substituting. 2 times, and we'll use 9.8 now, times 1.8 equals a half times 2 times v squared. Now, in actual fact, the mass wouldn't matter, just as we were discussing at the end of the previous question, because I could just cancel out the 2 from both sides at this point. But if you don't put it in, pupils tend to feel a wee bit uncomfortable with that, just cancelling out the m. So we'll just do what arithmetic we can. So 2 times 9.8 times 1.8, 35.28. But don't worry about significant figures in the middle of a calculation. A half times 2 is just 1, so that is just v squared. So swapping sides, and then taking the square root of both sides to get the answer. It's 5.94 meters per second. Question 34a is asking us about potential energy. So what do we know? We've got the mass. We've got the height, it's 20 centimetres, but we want that in metres, so divide by 100 to get into metres. And we've been asked the potential energy. So we would be expected in an exam to fill in G, although remember it is given in data sheets at the start of the multiple choice paper. 0.5 times 9.8 times 0.2, and that gives us the answer. .98 joules. What will be its kinetic energy at the lowest point? So a pendulum is this idea of swinging, and I've showed you a wee video about changing between potential energy it has at its highest point, and that would convert to kinetic energy at its lowest point. So its lowest point is minimum potential, maximum kinetic. So basically all of that potential has converted to kinetic. So the answer for the kinetic energy at its lowest point is simply the answer that you got for the potential energy in part A. So it's 0.98 joules. We can then use that in part C as our value of kinetic energy, because this idea of maximum speed, well, that would equate to maximum kinetic energy, which, as we just discussed, is at its lowest point when potential is converted into kinetic. So that's what we use for an EK. We've got our M, and we've been asked the speed. So no, we don't have a specific formula for maximum speed, but if we've worked out what the maximum kinetic energy is and then we can substitute that into this formula. We'll get the maximum speed. So 0.98 equals a half times 0.5 times v squared. Simplify what you can. Swap sides. And then get v squared on its own. And then take square root to get the answer. And rounding to appropriate numbers, significant figures. We get the maximum speed as 1.98. And then it kind of asks us for the explanation that we've been discussing as we're going through. Probably been better if this had been a wee bit earlier. So this is the maximum speed. Oops. This is the maximum speed because the lowest point is basically what we take as our zero height. So it's when all potential energy has converted into kinetic energy, i.e. kinetic energy is a maximum because kinetic energy depends on velocity and mass, but the mass isn't changing. Kinetic energy will be a maximum when velocity is a maximum. We'll go into a new page for question 34. And 34 is the same sort of idea, except instead of starting by pulling something to the side, a pendulum type shape, a swing is a pendulum basically. Instead of starting it from the side and then letting it go, we're starting it from the bottom and pushing. So we're starting it with kinetic energy, that would then convert into potential and vice versa. So it doesn't matter what point you start, pendulums have this idea of converting kinetic to potential and backwards and forwards between the two. So for this one we're given a mass and the velocity, and we've been asked a height. So once again we're going to base this on the idea that the potential energy and the kinetic energy, right, to the potential energy at the top, the highest point, will be equal to the kinetic energy at the bottom, the fastest point. So formulas, we can substitute in for both these values. So that's not very well drawn. And then we can start substituting in values now and get a value for h. So 60 times 9.8 times h equals a half times 60 times 3 squared. If you prefer, you can do the EK as a separate calculation, get an answer and then plug that in. If this doing it all in a winner, if you find that difficult, but you get the same answer. So simplify what you can. So I'll do the 60 times the 9.8. So I get 588 times h, and then I do the 6.5 times 60 times 3 squared equals 270. Remember, it's important when you're showing a substitution into that half mv squared formula that you show it as 3 squared and then do your working, because if you put it straight in as 9 there, there's a chance you might make a mistake, and if you've not got clear working, then you can't get credit. Now get h on its own, and you get the final answer then. .46 metres. I'll give this answer to 2 significant figures because the data given in the question wasn't as much, but if you gave it to 3, that would be acceptable. Now we made an assumption right at the start of that question that all of the kinetic that you gave with your push would be converted to potential, and then we've been asked a wee bit about that in reality. Why wouldn't that happen? So some energy would be lost, and we pretend to put that in quotes, to the surroundings. So identify what energy is being lost, where it's going, and why. So it would be a mixture here of the air resistance of the person actually moving through the air, and there would be friction in the point where the swing joins. Okay, 35 is really the first example, and it could maybe make it a wee bit clearer. It's the first example where we're including the energy loss stuff in our calculations. So we're not going to assume in this question that all of the kinetic converts into potential, because if you read through the question, first of all, you see that E is asking you about friction, so we're also taking account of friction. It's going to become part of our answer. So we just deal with each bit on its own. So A is asking us about kinetic energy. We've got a mass. We've got a velocity at the bottom. We do have two distances involved. Okay, these aren't going to actually be relevant to this particular part of the question, but we'll list them all anyway. We've got the distance down the slope, and then we've got a vertical distance, so h for height. So the formula for kinetic energy, well, we've got the mass and velocity, so that's fine. We can just go ahead and plug that in, and we'll get our answer. $108,000 joules. That's how much kinetic energy I had at the bottom of the slope. For B, I've already listed most of my variables, but I'm being asked the potential energy. So let's say we're not doing a conversion, we're simply going with the formula. And we have everything we need for the formula anyway. That's the simplest way. We know the height is 10 metres. So plugging all that in, we get our answer for EP. EP, sorry. Is 147,000 joules. So see how much energy is unaccounted for. So basically you had 147,000 joules at the top of the slope, but you can only account for 108,000 joules of kinetic energy at the bottom. So the kind of lost energy is the difference between those two, which is 39,000 joules. What would be the main type of energy? Well, it mentions friction in part E, and you should know that the main type of energy produced, right, heat energy. That's the main type of energy there. And then we're going to need this answer just about the force of friction acting on the carriage. So basically friction has caused this difference in energy that we've seen between the EK and AP. So the difference is 39,000, so we need that for the next part, for part E. So that is the energy that's been transferred due to friction. Right, so that's a work done by friction, 39,000 joules. We're being asked the force of friction, and remember, I'll just put it in again on this page, but we listed the length down the slope, So that is the distance over which the friction is acting, is given by 30 metres. So we can use the EW equals force times distance. So if you've got a question which has been about energy and then asking you about force, then remember your EW equals FD formula that links energy and force together. Substitute what you know. Swap sides and then isolate F on its own. And we get that the average force of friction is 1300 newtons. Then question 36. And we've been asked about kinetic energy. We've got the mass of the car. And we've got the velocity. So notice we use a metre per second value. And we've been asked EK. So fairly straightforward. And plugging all that into your calculator gives you the answer 200,000 joules. And then part B, the maximum braking force is 5 kilonewtons, so we're now introducing a force. Convert into standard units, newtons. And we've been asked about a braking distance. So once again we're linking energy and force. And the work done, well, if you're braking, and it doesn't make it that clear, but obviously you're talking about braking distance of a car, you're talking about it coming to rest. So if it had 200,000 joules of kinetic energy, the change in energy to bring it to rest is 200,000 joules. So the work done is 200,000 joules. The force you're told is 5,000, and rearranging then to get the distance. Divide both sides by 5,000. Just about fit this in. And you get your answer of 40 metres. Okay, for part C, if the driver has a reaction time, so we've got a time there, and what we've got to get is this wee bit idea. What do we mean by reaction time? Well, we mean the time that the driver will take to actually respond to hit the brakes. So during that time, they've not braked yet, so their velocity will be 20 metres per second. And you're being asked about this distance. So this is just a distance speed time. If they've not started braking, we're going to assume that their velocity is roughly constant. And don't forget, distance speed time is one of the most commonly incorrectly remembered formulas. Always check it against the formula sheet. And you get the distance during braking is 14 metres. During reaction. And we had that during braking it was 40 metres. So the total distance travelled during stopping is the sum of both of those answers together is 54 metres. And then we have to repeat it all again, except this time we're going at a slower velocity, and we're going to comment on that at the end. So the slower velocity is down to 10 metres per second. Still the same mass. So calculate the kinetic energy. And because we're squaring the velocity, previously it was 20 squared, this time it's 10 squared. Halving the velocity, because it's squared, ends up with a quarter of the energy. So right at the start, this car that we're going to try and stop only has a quarter of the energy that it did with the car going at twice the speed. Once again, we've got our braking force 5 kilonewtons converted to 5,000 newtons. We bring asked our distance. The work done is the force times distance, and same idea again. If you're braking to rest, then the work done, the change in energy, is the full 50,000 joules. Rearranging, so swap sides first of all, and then divide both sides by 5,000, and this time we get the distance of braking is 10 metres, so it's a quarter of the distance of braking, and that's going to be important. We'll get to our discussion. For C, we've still got the same reaction time, but our velocity is 10 metres per second. So the thinking distance, as it's often called, d equals vt 10 times 0.7. So by going half at the speed, your thinking distance is halved. And then your total distance is your 10 plus 7 equals 17 metres. So you're asked to comment on the differences and making reference to 20 mile an hour speed limits near schools. So we can see that the overall stopping distance is significantly smaller for cars at 20 miles per hour. The thinking distance is half, and the stopping distance, braking distance, because the stopping is the thinking and the braking together, and it's a quarter. Of the values at 20 metres per second. 45 miles per hour. This means that a car is more likely to be able to stop if a child runs out, and if it is not able to stop in time. So if an accident does take place, the much lower energy is involved. Mean that the child is less likely to be seriously injured. Yeah, I think the official statistics are something like at 20 miles per hour compared to 40 miles per hour. There's something like a tenth of the serious injuries caused. Okay, question 38 about roller coasters. And for each of these it says explain, so it's not just stating, explain. So for A, point A is the point of maximum kinetic energy, maximum potential energy, quite simply because it's the highest point. Potential energy varies directly with height. Mass and g are the same, they're constant throughout. Point of maximum kinetic energy is point E. It's not quite enough to say just because it is the lowest point. You say, why does that matter? Because it's the lowest point. So more potential energy has converted to kinetic energy. Okay, at point C, so at the top of a loop, so potential energy will be high it's not the highest point, but it's high up. Remember, you've got the same total energy to spread between your potential and kinetic. So kinetic energy will be low. And then lastly at point D, at point D, potential energy will be low down so more of that potential energy has converted to kinetic energy. Question 39. We've got a mass. We've got a height. And we're being asked EP. That's straightforward. Substitution, EP equals mgh. And plug into your calculator. Now there is actually more digits in my calculator, but I'm rounding to 3 significant figures. Alright, just watch that one. So what happens to the potential energy as it descends? So as it descends, that means the height's getting smaller, so the potential energy decreases. Now you didn't actually need to put that explanation in because it didn't ask to explain, it just said describe. So the potential energy decreases would do, but I've given you a reason for that, and it's converting to kinetic. And so we assume that all of that potential energy converts into kinetic energy. The kinetic energy at ground level will be 7,060,000 joules. So we assumed all of the potential energy to kinetic energy no friction or air resistance causing energy loss. And when a bobbin stops at the end and breaks, what happens to this energy? So brakes use friction. So the energy is converted into heat in the brakes. And that heat would then be lost to the surroundings. And then last one, number 40, we're just about estimating. So what's a reasonable mass for a car? Well, most cars are about a metric ton, about 1,000 kilograms. You know, somewhere between 600, some cars are up towards actually 2 tons, but somewhere between about 600 and 2,000 would be a reasonable estimate for the mass of a car. We need to get a reasonable value for velocity. Now most of you will know this okay in miles per hour, but in meters per second, maybe not so sure. One of the earlier examples we did, 45 miles per hour is about 20 meters per second. So, you know, somewhere between with 10 and 30 meters per second would be reasonable estimates for a normal car. And we're being asked to calculate the maximum energy. Now it doesn't mention what type of energy that would be, so you're expected to get the idea that although it's talking about the braking, the energy that's available is the kinetic energy it had in the first place. So we're not going to do a formula involving braking. You could approach the question that way. Some of these open-ended questions allow you. So could you estimate a braking force? Could you estimate a stopping distance? But I wouldn't expect you to not be able to estimate them that realistically just off the top of your head. So I think this is a better way of approaching it. We've got a mass, we've got a velocity, so we can just substitute in to our equation and we get about 200,000 joules. Now that's the amount of kinetic energy that's available. That would do as a reasonable estimate. You could go on to talk about the idea that, well, could you really store all of that? So maybe realistically you could only store half of it, or even just a quarter. But that answer would do for now.